understand that the reflections occur anytime you have an abrupt change in the medium. So these diagrams show this, and I'll show this to you in class, and we'll do this, okay? But if you have a fixed end, notice that like an up pulse comes in and that we actually get a down pulse, right? So a fixed end will actually invert the reflection, but you do get a reflection, right? Even a free end, so if we've got this medium and it can move, it's free to move up and down, a free end will actually reflect. And free ends actually reflect upright. Okay, light, obviously light reflecting off the windows, the Empire State Building, off water, right? If the water is totally still, you can get a perfect mirror reflection. This is light reflecting off of a metal coating on the bottom of that mirror. This is a partial reflection, right? So glass will partly reflect, partly transmit the light. And then, of course, if the water is absolutely still, you can get these beautiful mirror reflections like that. Sound will reflect. We used to stand on our hill in Wisconsin and shout across the lake, and the sound would echo. Of course, we'd always yell "echo," and then it would yell "echo" back to us, right? This is a church, I believe, that we sang in choir in Los Angeles. I could be wrong, though. But anyway, all these nice curved concrete surfaces cause a lot of echoes, which is a lot of reverb. And there's certain music that really likes reverb. So this is the St. Paul Cathedral. I actually sang a piece in here, and the conductor had to adjust the tempo because there were certain tempos that sounded good, certain tempos that didn't sound good. This is, of course, Notre Dame. And there are signs, by the way, in Notre Dame saying, "Don't sing." I wanted to sing. I would have sung church music, right? Okay, more examples. It turns out that Polynesian navigators can actually see wave reflections off islands that are themselves over the horizon, which is absolutely outstanding. You and I can't see them because we haven't trained ourselves to see it, but these guys can navigate out of sight of islands and see shadows of islands and reflections from islands. Long distance phone calls. I call my sister in France, right? And there'd be abrupt changes. The US phone system would change over to cable or satellite, which would change over to the French phone system. And you'd say, "Hi, hi, hi, hi." You get reflections, boom, 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 right? And generally what you do is you'd hang up and try to get a different connection, right? But, reflections in long distance phone calls, right? And there's two ways to prevent reflection. The first way is to make there be no change in medium, right? So go invade France and make them use our technology, right? Okay. The other way is to make the change less abrupt, to make it more gradual. So, for example, if you have a 8-ohm stereo and a 4-ohm speaker, you can go to a store and get an impedance transformer that gradually changes it from 8 to 4 ohms, and then you won't get a reflection off the speaker. Reflections are bad in this case, right? More examples. I've got a demonstration. Coatings on telescope lenses actually slow the light down more gradually because the light slows down when it reaches the lens. That reduces reflections. It's also a little more clever than that too. And then acoustic impedance transformers, I'll demonstrate that. That's a big word for something that you already know what it is, right? And then these things on the horns, right? The bells on a horn, these things, that's a bell. Right, that thing gradually goes from narrow pipe to, that's the cross section of it, right? Goes gradually from narrow pipe to wide open room. If you take that bell off, and I actually have a trumpet, it's like a Boy Scout trumpet. If you take that bell off and blow, it's just like no sound comes out. Almost all the sound vibrates back into the tubing. This is an anechoic room, so this surface is designed to gradually absorb the sound. As the sound goes in, it bounces, 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 and doesn't come back. What's funny is when the tour guide talks to you, if they turn their back to you, you can't hear them because there's no reflections. The sound has no way really to get to you except for diffracting around the person. And then, we talked about this already, but if you have a fixed end, that is, if it can't move, then it will invert. Now, by the way, light traveling through air and striking glass, that's like a fixed end, or striking water. Anytime it like slows down, right? So if it has to slow, if this is slow, then it will invert it, right? If light is traveling in glass and it reaches a boundary where it goes into air, right? That's like a free end and it will not invert. Okay, and we'll use this idea later, right? So free ends do not, or if it's freer, right? I'll put freer, fixeder, right? So in general, if the wave slows down in the medium, that's like a fixed end, like this new medium, right? If it slows down when it gets there, that's like just like a fixed end. Okay. And then, geometric, we're not going to get into geometric optics. Notice that the angles are measured here with a line. We'll do this when we get to refraction. We'll actually measure if it refracted into this thing, right? We would measure these angles actually like this. That's just a thing that they do in optics. Okay. And then I've got a demonstration that I need to show you, right? And I think that's all we need to say. This is just another example of that. This is an uneven surface. Notice that all of these angles of incidence and reflection are the same. It's just that the surface is all bumpy, so it doesn't make a perfect image. Yeah. So most objects are not mirrors, but if they are mirrors, then you get a perfect image like this. And that's it.